I will start with tutorial 1, then we continue with lecture 3, and I hope lecture 4 will see if it's not postponed to Wednesday, but we still have 3 more days, so no issue. So this tutorial 1 is the wall related only to radar signal processing, ambiguity function, blind zone, and all these things that we discussed yesterday, because I think that is important. I try to make all interactive, so we don't need any coding, anything. We just run it and you can check it. What is useful for you, that I already sent you all tutorials, so you can later change any parameter and just check it results. You can use it anytime when you want, so I hope that will be helpful. So today first, before we start MATLAB tutorials, I will show you some details about spectrum allocation and utilization only at India. So in case that you won't make any outside measurement, what you need to do. And of course, bureaucracy in every country is huge, so there will be a lot of tasks that you need to pass through to get permission for outside measurement. Then we will discuss blind zone, instrument range. It is relatively easy. Then range measurement, I will show you results for rectangular pulse, L04 pulse, it is mean linear frequency modulated pulse, and visualization of pulse compression. So it will be like comparison of these two pulses. Then I will show you range resolution capability. So it will be based on the resolution of two targets, if it's distinguishable or not. In main lobe, unambiguity of range measurement, radial velocity measurement, it is connected with blind speed, and then radar equation and range quanta and Doppler sampling. So it is our slow and fast time. So quite a lot of tutorials, so we'll see, we will continue. I also later will show you these slides, so even if we will not finish all, you can easily just run this PDF and check individual scenarios with MATLAB. So it is up to you. In case that you will have any question later, even next week and so on, just contact me through email or through WhatsApp group or anything. So I am available, there is no issue. So, what about spectrum allocation? Of course, there is some global spectrum allocation. It is defined on big conferences, but you will not touch with them because it is like on national levels. So each country, I think almost any country in the world is participant in this spectrum allocation, except maybe few small countries. This global spectrum allocation put entire frequency bands from, I think, 3 kilohertz up to 300 gigahertz. So of course in this upper sides there is almost not any services. Why? Because it is so huge frequencies that until yet we don't have so many devices that working in this high frequency range. And what is important, in any service, in any allocation in frequency spectrum, we have always two columns. It is primary and secondary allocation. Primary, it is mean protected. It is priority. It is mean like GSM service. It is priority, and this like GSM service, some mobile operator has priority for this frequency allocation, for specific allocation, and nobody else can't use it. Then is so-called secondary allocation, and it is without protection. But there is one important thing. must not interfere with primary allocation. So, okay, secondary allocation can be used for some service, but can't be conflict with primary allocation, if you get my point. So, you can use it if you have permission, of course, but be careful, you can't involve this primary allocation. So, definite globally, it is ITU radio regulation, so call it RR, and it is updated in WRC conferences. This ITU, it is International Telecommunication Union, is divided to many different sectors, but we are interested now only in ITUR, it is radio communication sector, and part of this radio communication sector is so-called Radio Regulation Board. And this regulation board consists proposing rules for the allocation in frequencies. Okay, there is from 9 up to 400 gigahertz, some tables are from 3 up to 300 gigahertz and so on. I think that this small differences is caused by national allocations table, because I know that British, they have it from 3 up to 300 gigahertz, we have little difference, so it is like varies, but never mind, in 9 kilohertz there is not so many services, it is very low frequencies. At 400 gigahertz it is too high, so of course, like GSM, we have two bandwidths, 900 approximately 900 megahertz and 1.8 gigahertz, DVB-T and other services working in other. So radar working, how I already mentioned, it in bandwidths S, L, C or X. We are focusing now on C and X. If I will continue, there is some utilization models. So the utilization models is divided to 3 different brands. It is individual licensing. So it is individual licensing. You get license for specific band, for user, station specific assignments, often with coordinates. So it is geolocation for some. What is important, you need to fulfill EIRP, so it is isotropic radiation power. So it does not mean that you get permission for some specific bandwidth, but of course there will be limitation in your emission power, because it is difference if we will use transmitter 1 kilowatt or 1 megawatts, of course, because if we will use higher power, of course your range will be much higher, so you need to be careful about this. So it does not mean that you get permission or you paid for permission, use some bandwidth. There is limitation, of course, in power. There is more limitation, but it is limitation in power, antenna pattern, emission mask, and so on. Then is group shared licensing. It is like national PPDR. It is public protection and disaster relief. Imagine if will be some earthquake or something like this. Of course, like government needs some radio frequency that will be, in this case of some disaster, available almost everywhere and will be free for this emergency cases. And last one is general license exempt. It is strictly limited to SRDs. It is short range devices, and it is mean like Bluetooth or something like this. There you don't need, it is strictly limited to some really short distances. So it is like general license exempt, so you can use it almost anywhere. Of course, if we all of us use, I don't know, Wi-Fi in same frequency, there will be some influence, but honestly, who cares? It is our problem, if I can say. So, but it is some, I don't know, Bluetooth, it is some other similar services like this one. Okay, then transmission regulation could be channel based. So in some specific frequency bandwidth, you get only, like example, 1 channel permission, 2 channel, 3 channel, something like this. So it is depends on your service, of course. So you will get fixed channel and you can use it just this channel in this bandwidth. Then it is regional base and it is geographic restriction. Okay, you can use in Assam, you can use in Delhi, you can use in Mumbai, and so on and so on, because there is not influence between these things. Then it's point-to-point, like sensing, and it is depends on site coordinates, azimuth, and again radiated power. What is mean? I don't know if it's in Czech we have like example coverage by high-speed internet with some point-to-point access, because if you have some small village, some small village that is not close to any city and you need high-speed internet, there will be some like access point from from city to this village with line of sight, and you can use it just in direct azimuth transmission in specific power and only between these 2 points. It is useful because it you not influence anything else, and it is just like point-to-point access. But of course, for us in this case will be most important individual licensing, because you won't go to somewhere where is wind turbines, where you want measurement. And of course, you could get this permission, it could be only time limited, like for 2 days, 3 days, 1 week, I don't know, some like this example. Of course, it is a little tricky, because imagine that you will get permission and there is no wind for the whole week. Okay, you pay for permission and you not make any measurements, so you need count in this also. Okay, who is responsible about spectrum allocation? Again, globally ITU R or VRC, this conference, then regional, and now it is divided in Europe, it is CEPT or ECC, in Asia Pacific it is APAT. By the way, all this red one, it is interactive link, so if you will click it, you can open web page and get more information. So for this reason it is interactive. And in the Americas it is CITEL. So they use it for harmonization, common position, technical derivables, and so on and so on. But you are more interesting not in regional but in national regulators, of course. And now we are in India. In your country. So it is implementation of the national table, issue license, enforce. In India is WPC. We can just open this link. Okay, give me a second. It is not easy, I need to move. But I am connected. Yeah, I am connected. Oh, yesterday I checked it and working. Maybe some connection issue only. But yesterday working fine. I'm sorry about it. So and then this one. Yeah, I have it connected Wi-Fi, unfortunately, to Eduram. Oh, you don't see it. I see it on my second screen. So it is okay. And just before 1 minute I sent you email with tutorial, so my Wi-Fi is okay. Okay, I have downloaded manually. I expect maybe some problem. So I will show you your allocation table of your country, how look it. So it is national frequency. Okay, it is National Frequency Allocation Plan. It is from 2022, and there you can check wall allocation that is available in your country. So I will go down. So you can see there is division to some region. You are in region 3, and this is some general things. Okay, and now you can see this allocation table. So we will go to first number. It is always frequency band. It is like primary and secondary usage, how I already explained. It is a huge document, of course, because it is true, and it is very often updated, so you can check it later. It is 1.6, 1.8. We go for some interesting frequencies for us. 4 gigahertz. Okay, radio location about 5 gigahertz. You can see, and so on and so. So it is, I don't want to say boring table, but you can see everything where is everywhere. So it is just this PDF. You can download it from a link that I provide. I don't know why today not working, yesterday working. I already checked everything. But if you want, I can send you this document also, so you can already check it. And also, please, in tutorial you will have there links and citations, so you can easily find it also, this document. It is publicly available, of course. And there is in X-band example of, you can see radio location, radio navigation. So it is our radars in X-band. So it is just from 9.3 to 10 gigahertz example. And it is for each region and for India specifically. So you can check it easily. So there is like summation why we can just show up and measure wind turbine echoes, because we need right band, on which depends right band, of course, on our devices, on our radar or software-defined radio and so on. I don't know if you have experience with SDR, but we usually use some SDR from National Instruments, and I will show you someone. It is devices like these devices, 1 kilo maybe, and it is really powerful. It has transmitter, receiver, multi-channel, and so on. It is also relatively expensive, but if you compare with price of radar, it is very cheap. I think that this, of course, they have multiple models, but price vary about 8 up to 12,000 euros or something like this. But still, if you compare with millions for radar system, it is still relatively cheap. Then you need, except right band, of course, license and authorization, regulatory site clearance. So it is site approval. Okay, you get transmission that you can transmit, but you need site approval. Okay, you can go to this exact place with permission, and from this place I can start measuring for installing this radar station or for measurement. Of course, if it will be classic radar, you need a lot of more document than if it's just temporary one-time measurement. It is much easier. But before you go to these authorities, you need to prepare complete documentation of your setup, it is clear, because they need to know what you will transmit, which signal, which power, emission limits, duty cycle. It is also important because we make measurement in pulse regime. So it is duty cycle is 10%, 5%, 90%, continuous. Do you understand me? And also it could be possible time or geography restriction. Imagine if you, what is possible time restriction? During daytime, maybe somebody use frequency somebody else. So you can't use the transmission during daytime, only during nighttime or something like this. And geography restriction, it is clear, it is with geography where you is your location. So all this you need to fulfill before you go to make a measurement. And I think that get permission is not easy task. It could take a month of work. So there is step by step what you need to do. Choose band consistent with your measurement goal. So you look first to document. Apply to WPC for temporary or experimental license. You need to tell them center frequency, so it is your carrier frequency, peak, mean, radiation power, antenna gain pattern, geographic area, where you want to measure, and schedule when. And you probably fill some form, prepare some document, and put to authorities and wait for answer. Then you obtain from SECFA, it is Indian like authority that give you this clearance, sitting clearance for any fixed site, and adhere to aviation high keep out rules. Also, you need to protect primary users in case that somebody uses this frequency. Like 2.7 to 3, it is protect aeronautical radio navigation or radio location. In 5.6, it is for weather radars usually, and 9.3, 9.5, it is maritime meteorological aids use, and so on and so on. So you can see it is exactly our frequencies that we are using. It is good use same frequencies like your radar. Why? Because your measurement will be exactly valid and will be same reflection on same frequencies like measures your radar. So we use it, this national instrument SDR, and it is in S-band about 3 gigahertz, how you can see later, I think tomorrow. So if you confirm spurious out of band EMC limit in the license, duty cycle, and so on, you get clearance and you can go make a measurement. Only there will be some exception if it will be close to national border or some special areas, of course military. There maybe will be much more difficult to get it. And unfortunately, big wind turbines farm, it is somehow protected area, but you understand me, because it could be if somebody destroy it like terroristic attack something, it could destroy power in the whole area or something like this and cause it a lot of problems. But we not be pessimistic that we are close to national border and we are inside country and not will be so bad. Okay, there one quick repetition about radar signals and we will move to MATLAB. So it is our transmitted signal, it is PRI, all this, it is pulse repetition interval, then is next pulse repetition interval, and we are pulse transmission, and go, and we continue. Then we have CPI, coherent processing interval, it is this called slow time, and you know why, because we need compute spectrum. So we are sending multiple PRI, like one example 1000, and then we in slow time compute spectra, which is in how to say, 1000 frequency line, because we have 1000 samples. It is like this. So what is important, it is blind zone. So just for repetition, blind zone is a zone where I can't receive any signal because I will destroy my receiver, because reflection in case of target will be so high that will destroy, because receiver must be extremely high sensitivity, because he detecting so small attenuated signal that must be very sensitive. Then we have instrumented range. So it is, how I can call it, listen time, when our receiver listen if he gets some answer or no answer, and it is mean no target and it is just noise answer, or reflection from environment. It is always reflection from environment. And we use it words clutter. It is special words that is used for reflection from environment, clutter. C-L-U-T-T-E-R, clutter. Because this word has also another meaning, so it is little unusual. Then we have dead zone, and dead zone we use it for changing to another pulse regime, or for diagnostic of our radar, and so on and so on. Everything what you can imagine. So we are receiving only in this, not small part, in this part, reception period. So now there is typical example. By the way, these values are from our measurement, from real measurement. So we use SDR NIX310. It is about this 10-12,000 euros devices. I will show you all details, what is structure of this, what is block scheme, but later when we designing measurement chain. And what is parameters of our measurement? Carrier frequency was 3 gigahertz. So wavelength is 3 centimeters. Pulse width is about 200 nanoseconds. PRF, it is 2 kilohertz, so inverse value is PRI in time. Sampling frequency is 40 megahertz, because everything what I show you there is continuous. But of course, remember, after I receive analog signal, first thing is AD conversion. We are working with samples. But if I will draw this picture like in discrete time, it will be more confusing. So we are all picture using in continuous time, but we are working with samples. Still, you need to have this information in your mind. Where is my mouse? Okay, this. Then duty cycle. So if you see that pulse width is 200 nanosecond, it is this one. PRF is 2 kilohertz, so my duty cycle is only 4%. So only 4% I'm transmitting, and about 90% I receiving echoes. And last 6% it is this dead zone, or 10% it is depend. Recovery time we set to 0, and guard interval is 0. What is this? I can say easily that is some time for recovery and guard interval, protection of my receiver and so on. But we can include everything for simplification to dead zone. Or you can see this one, this blind zone, it is not exactly at to end. So it is some guarding interval, something. So, but let's put it to dead zone, everything. I just want to show you that there is more deep, some recovery time, guard intervals, but you can see I set to 0 because I don't care about them now. So what will be blind zone? So minimum range where I can detect target. For me, based on this parameter, it is only 30 meters. Oh, it is it is not so bad, because from from 40 meter, 50 meter, I can easily receive reflection for target, but not until 30 meters. What is maximum unambiguous range? So it is only limitation of pulse repetition frequency, and it is speed of light divided PRF. It is approximately 75 kilometer. Don't expect that will be 75 kilometer. No way. It will be 10 kilometers. It is depends on your power also. You remember, this is just theoretical. So 75 kilometers. So it is clear that after that I can measure only between 30 meters up to relatively 75 kilometers. Far, it is too far, and close, it is too much close. It is in 2 mile zone. So what is instrumented range? It is listen time. It is listen time, this one, and it is PRI minus tau plus T-res, but this is and guard interval, but this is 0, so it is about this almost 500 microseconds, so it is 4.9 kilometers something example. So it is clear that is almost like unambiguity range, because this 30 meters, it is not so big limitation, but it is in theory. So we of course make sample to range spacing. So we have several digital samples in one theoretical resolution cell. If you have resolution cell, it does not mean that in this cell is one sample. There is multiple sample. I need more information, not only one value about one sample. It will be constant. It is not almost any information. So there is more samples. And how is fit with my calculation? So range resolution we already calculated of uncompressed pulse. It is depends on tau. It is length of my pulse, and it is about there. So so we have several digital samples within one theoretical range resolution cell. This does not change the physical resolution. It is just more multiple samples in one resolution cell. So this physical resolution is set only by bandwidth of pulse. So be careful about this. Not by length of pulse, by bandwidth. We yesterday derivated these things. So what is sample to range spacing? My sampling rate of this continuous signal that I receive is 40 megahertz. So delta R of sample is C divided to F, so it is about 3.7 meter per sample. So you can see my resolution is 30 meters, but this is about 3.7 meter per sample. So it is mean approximately I will have 7 samples per one resolution cell, something like this. So unambiguous radial velocity, okay, we can also compute is 50 meters per second. And now my question will be, what do you think with this? If we will have target and 3.5 kilometers, are we inside instrument and unambiguous range from point of view samples and all setting? We are in the right way. Can we start measurement, theoretical measurement, because of course there is still not power. So we will measure what is time delay of target. So it is 3.5 kilometers. So time from transmitter to my target wind turbine and back will be about 20 microseconds. So fast time sample index will be about 801 samples. End of transmission pulse, it is about 8 samples. So if I will get this value minus this value, I get this value. So answer, if we are in range, yes. of course, because it is between 30 meters to 75 kilometers, so is it clear? But with this example, I want to show you how you can easily compute. This is not any magic. It is only few formulas, and you can easily check it. You can even check if you don't like your resolution under one cell. Okay, make a higher sampling frequency. Of course, higher sampling frequency is more data, and you need to store somewhere this data. And I must say that your hard drive really fast disappear because it will be full. Because imagine that it is number of sample per second, 40 million, but I don't resolution of quantization, it will be about 14 bytes. So 40 megahertz multiplication by 14 bytes, it is size of data per 1 second. Honestly, we made about, I don't know, 20-25 measurement, and we have about 8 terabytes of data, and it is only few measurement, and one measurement is about from 8 up to 15 seconds. So we have only 2 rotation of wind turbine, and it is gigabits of data. So, and if you need to pre-process all this data, oh, it is for days, because you understand me, it is not hard computation, but just this data throughput, you need just process all this data. So we always pre-processing all this data, and what I will show you later with our real reflection, it is already pre-processed, because if I will give you raw data, my notebook just will die, because it is not possible to compute. We have some PC station with 128 gigabytes of RAM, big hard drive, about we have like hard drive, how to say, storage that has about 80 terabytes of data, and we can like written speed is about 1 gigabit per second. So even if your SS drive, it is very slow, so there is about 20 SS drive that is connecting in parallel, and the data just flow to this drive. So it is really huge. But I think that is clear, because so you can't make high resolution with sampling frequency, but be careful. It's your amount of data start be really exponential growing. It is really huge. But in present time, it is not so big problem. You can do it. So now we open first script, and please change, just play with this. I will show you, of course. Change PRF, change PRI, change pulse width, GAR interval, and watch the result. It is best one. Of course, I will show you some settings, but it will be nice if you can play by own. So I will switch. Okay, my eyes is not so good, so I will close. We don't need. So check it. So there is some definition of variables only: speed of light, carrier frequency, wavelength, PRI, inverse value as PRF, length of pulse, recovery time, sample speed, where is target, it is simulation of target, what is echo amplitude, it is also simulation, and everything you can change it, and always you get another result. And what is signals to noise ratio, because of course if it will be without noise, what will be answer? Always one line, where is target? So if I will run it, you will see always something like this. So it is my echo, this is noise, of course, and this small thing, how you can see, it is blind zoned, because it is only 30 meters, so it is small. but you will see details only first 5 kilometers. But what is full span? Oh, sorry, I don't. Okay, it is 75 kilometers. And now in command window, it show you all results just to be comfortable. So minimal blind zone, instrumental zone, sample spacing, target. It is time delay of target. It is t but not tau, but never mind. Which index of sample, and it is all. And you can just run it. You can just please for 2-3 minutes just play it, try change. I don't know, PRI. We can or we can, yeah, pulse repetition interval. We can make 1000. Oh, sorry, check keyboard. 1000. Tau will be only 20. So if it will be shorter, what will happen if we will continue? Target is still in 3 gigahertz, and check. Now, because I change in blind zone, it is not 30 meters, it is only 3 meters theoretically, but unambiguity range, because I change bandwidth, it is 150 kilometers, spacing, and so on and so on. So please just play it, try it, and I will switch and to this, and there is what you can see. So if you increase pulse repetition interval, what's happen? It is clear, it will be instrument range will be longer, so it will increasing my unambiguous range. My radar will see to longer distance theoretically. I think that is clear, and you can play with this. It is like you can also you can change signal to noise ratio. If you are increasing noise, your target will slowly disappear this amplitude, of course, because it will be masking in noise. If you changing guard interval, you can try it. If you increase your guard time, changing pulse width. If you will increase longer pulse, radar resolution becomes worse, of course, and blind zone will become larger. So we can change it. If we will change, where is it now? So it will be not 20 nanoseconds, but I don't know, 500 nanoseconds. You can see it is now 75 meters blind zone, instrument range 150, again, of course, because it is not influenced. So what is important? PRI and tau, length of pulse, and the rest is speed of light. It is still same. Of course you can change it, but it is not so important. You can change it also. We can try like 20. We can put -20 dB. Okay, do you see? Almost disappear. So we know where is it, because I have put line there, but you can't recognize. So it is just easy evaluation and playing with these values. Is it clear, this one? But always check for full range. It does not mean that be careful about 5 kilometers. It is just details, because I need to do it this zoom, because if I will show you always this one, there is nothing visible. Okay, of course you can change also target and amplitude of target, but this is just for example if you are in the right position. Oh yeah, it is under 5 kilometer. It will be at 7 kilometer. Yes?
Sir, I have one question. Sir, one of the crucial thing is sampling rate.
Yeah.
it should be 1/2 divided by pulse width, right?
It is related to bandwidth.
Bandwidth, correct.
Be careful, not length of pulse, because if you use some modulation, then it's not tied with length of pulse. Of course, if will be unmodulated pulse, it is science function. You are right, completely right, because it is just inverse value of length of pulse. But if will be with inner modulation, it is another formula. It is divided to 2b. It is just strictly to bandwidth of this inner modulation, not length of pulse. Be careful about it.
My question was that if we do that calculation, that optimal sampling rate should be 10 megahertz, but you have chosen 40 megahertz.
Yeah, because of course.
This will increase the data output.
Yeah. Because you know. Usually we like oversampling little, 2 times, 3 times, 4 times, because always I make, if I want to process, I can always do it decimation if I don't need. But why we use it higher frequency sampling? Because in case that I need it and I don't have it, I need go make again measurement. And I don't want go to measurement if it's 150 kilometers far away from me. So we push frequency sampling rate to maximal limit what we can, because always you can make decimation if you don't need. But if you make like minimum sampling rate, just fulfill sampling theorem. And in case that you need higher, you need go to again outside to make measurement.
So what is the general rule of thumb? Right?
How many times should we take extra sampling? Like 1 time, 2 time, 3 time? 2 time is the theoretical limit. So
yeah, it is a hard question. Honestly.
Okay, sir, no problem. I'm just asking
it is a hard
because
question. I don't think that there is any rule of thumb.
There is no rule of thumb.
No. I don't know. We just try push it through. Okay, we use it 1 gigabits LAN because it was connected not of course to USB because it is 1 or 10 gigabits LAN network. So with okay. So we tried to push to almost to maximal sampling rates.
Okay, no problem.
So if you make more and more sampling, it is not harmful to anything.
Okay,
if you will make extremely large sampling, really 10 times, 20 times, then can be some dependency between sampling of noise, some correlation thing, but I think that you don't have chance to do it because you don't have so quick device to make so quick sampling. So we use it about 3-4 times more,
Okay.
but there is not any rule. Sorry.
sir. Okay.
It is bad answer, but
Yeah, no, it is okay, sir. Okay.
Okay. So we will go for another tutorial, and we go for range measurement accuracy. You see this similar slide yesterday, but
Okay.
I just think during evening about it, and I just want to give you some more explanation because there could be a little confusion, because this is since function, and you know that since function is, if I have rectangular pulse, it is spectrum. But be careful, this is since function, it is true. But it is cross correlation, there is time, it is not spectrum. It is little confusion why. I will just explain you, so I just during evening adopted this slide, because I don't want that you think that this is spectrum of the rectangular pulse. It is not true. And why? if I will have rectangular pulse, just rectangular pulse, my cross correlation is triangle, clear. Spectrum will be sinus function, clear. But now I don't use rectangular pulse, but I use L04 pulse, linear frequency modulated pulse. And definition of this pulse in time is this one. It is exponential jpkt squared for time duration of pulse. If you make visualization of instantaneous frequency, it will be linear increasing of frequency. Zero otherwise. So it is definition of this pulse. Received signal is transmitted signal that will be attenuated and delayed. Do you agree? Attenuation and delayed. Clear. Impulse response to my L04 pulse due to cross correlation will be complex conjugate minus t. So how looks like? It will looks like this one. So it will be impulse response for cross correlation. So I will compute received pulse with impulse response, and you get this function that is sinus function also. And why? Because if you will see spectrum of L04 pulse for, how to say, enough large bandwidth, not for extremely short bandwidth, for some kind of bandwidth, it will look in spectrum like pulse, but in spectrum. And if you make inverse Fourier transform, and in spectrum we have rectangular pulse, almost rectangular pulse, what we get in time domain? It is symmetry of Fourier transform. We get sinus function. So sinus function in time. Do you understand me? In time, if we have rectangular pulse, spectrum is sinus function. And due to symmetry, if sinus function will be in time, in spectrum we get rectangular pulse. So it is I don't know how you call it, this property of Fourier transform. Symmetry, duality. Duality. Okay. We call it symmetry or duality, so there is little confusion about words, but so we are in time. And it is time, and this you can see it is again cross correlation. This is cross correlation of rectangular pulse, and this is cross correlation of L04 pulse. So it is in time. I just won't make this explanation because I just really during evening. I hope that don't think that it's spectrum of rectangular pulse. No, we are in time domain. It is just for explanation. So you will see there. I think that is clear because Fourier transform is very well known everywhere. So and filtration also. So I just want to present you this one. Okay. So, and okay, last thing, what you see there, it is not in zero, maximum is not zero. Why is in tau d? It is our time delay, cross correlation. And from position of maxima, I can recognize, oh yeah, there is my time delay, and I can convert it to distance, and I know where is slant range of my target. And this is L04 compression, then we have L04 compression, then we have so many different Barker codes, and so on, phase coding. In the last slide of this tutorial, I have again application where it's about 5 different pulses, and you just can click and present results of this. So it is just explanation that that is not spectrum, all. Maybe it was clear from yesterday, but I was not sure. So, about range resolution capability. I already present you this picture, and you know if I have this sinus function, and if I can distinguish both maxima Perfect, good resolution, enough. But now I will show you that it's not so easy. In radar is anything not so easy. There is always some complication. So, imagine matched filter impulse response is essentially time reverse conjugate of transmit pulse. Do you agree? We just show it in previous slide. So, when we have two targets, we have two time delays. Clear. And how will looks matched filter output? This, this one, if we have two targets. Of course, it will be coherent sum of two shifted impulse responses, something like this. But it is complex. It is not real. So it is complex amplitude. So one complex amplitude, second complex amplitude. And when it's complex, it not is only amplitude but also phase. And sum of phase. So what will be results of this summation? It is depends not only on both amplitudes of targets, but also on different phase of this both complex amplitudes. And imagine if phase will be 0, then it will summation, it will be undistinguishable. If it will be 180, it will be two different main lobes. And how you can recognize which phase will be? It is random variable. It is depends on target or movement when you get reflection. So it is not depends only amplitudes of reflection, but also on difference phase between of these two targets, because it is complex amplitude. So if we assume the two targets are at different position, corresponding two delays with relative phase, we will ignore noise now. The difference between one complex amplitude and second will be delta phi. It is difference phase. So you can see it is one complex amplitude, second, and this is this difference phase. Of course, you can use phase 1, phase 2 and make differences, but I think that is better if I use just delta phi like difference phase. So even if this amplitude will be 1, this will be 1, different tau 1, tau 2, and you can say, yeah, I can recognize, why not? No. Unfortunately, it depends also on phases. So in some case, yes, you can easily recognize. In some case, no, you can't recognize because it will be summed together because it depends on phase. So if our phase will be 180, it is strong destructive interference between the lobes, and it will be deep valley between this one, and we don't have issue. And if will be phase 0, it is constructive interference, and you will see one main lobe. So it is not depends only on time delays. Of course, if will be time delay higher, you can recognize, and phase dependency not will be so high, because I don't care, it is so indifferent time delays. But if time delays will be closer, then this random phase start be important, and it is random, it is the worst. Sometimes you can hit good, sometimes you can hit bad. Okay, so open range resolution application. I will close this one. Okay, this one. This range resolution application, I still updating this application, and now didn't work only with rectangular pulse but also with linear frequency modulated pulse, non-linear frequency modulated pulse, and Barker. And you could set a lot of parameters and always watch results. So I hope that will work for you. I tested all application and works for me. Okay, it is works, but it is in my site. I am glad that you have this screen there because I don't need to do it this one. Okay, just run it if works for you. Check. There is controls, so you can easily. I will do it this one. I can't make to full screen because I don't see some border, so it is just. There you will see always pulse autocorrelation function. Maybe I can limit until -40 because it will be more detailed, but it is not important. You can see this is first side lobe, so it is, if I put a rectangular autocorrelation function, it is triangle, but it is in dB, so it is not triangle because there is, of course, not linearity, but it is triangle. And check, if I have two targets, there delta R is 60 meter, so it is it is first target, R1, where is location of first target, and this is difference between targets, if you get my point. Okay, I can put R1, R2, but I just do it the difference between targets because it is better. And recommendation, visible, if you can see, the resolution is about, for rectangular pulse, about 6 kilometers, so of course you can't recognize two targets, not any change. If I use L04, resolve it, yes. Visible 70 meters, and you can see, but it is hardly visible. You can see this is only what will be about 4 or 5 dB. It is not big difference. We are on the edge. And there you can then change L04, nonlinear frequency modulation. You can see there is bigger differences. There Barker. Barker in this case didn't work, but Barker has another advantages. I need to set up another parameters for this. So generally in waveform you can see this for waveform. By the way, it is modular, so if you want to put another waveform, just to put it, you can program it and put it, so it is modular. And there you have second option is scenario. Rectangular pulse, low resolution, L04, two equal targets, weak target in side lobe, sampling effect, and comparison L04 and L04. So it is like presets for individual scenario. It is just what I think that could be useful for you. So you can see now I have one target 3 kilometer. Difference between target is about 6 kilometer, so I can recognize both target, but it is 6 kilometer differences between targets. L04. Oh, there I have some. Okay. And there is visibility presets. So you always change scenario and visibility preset. If visible, non-visible, of course you can change it manually, but sometimes it's hard. It is a lot of parameters, so there is some hint for you how to use it. So check pulse length, sampling period, bandwidth is still same, and now it's visible. So it is visible about 70 meters. Will be visible, it is mean that will be 70 meters far away each other. Hardly visible 30 meter, and invisible until 11 meter. It is just, it is not exact value. It is just some presets that I want to present you, show you what you get. So is it clear? Two targets, resolution 67.5, and you can see. And there you can see the phase change. So we will put 0. Did you see how changing just phase, nothing else? So 0, it is the worst case, and I can still resolve. But if I will do hardly visible, this is almost not possible to resolve. Due to noise, if will be there noise, forget. One main globe with noise, no change. And check if I will put 90 degree. Do you see? Just phase, nothing else. And phase is random variable, so 180, it will be best option. Yes, it is. It is completely valid with my theory that I present you. If we put 0, no change. And if we, this is distance between targets, it will be 40 meters. Okay, one main lobe, no change. There is not two targets. Weak target in side lobes. What this mean? Okay, not Barker. We will put. Okay, we will. Okay, I know why is Barker. What this mean? Main target, big ship, big aircraft, and then some really small aircraft. For acrobacy, something really small one. The amplitude is small. And what's happened? Sometimes strong target could mask your weak target. So in case that I will changing value and will go close and close, this slope will continuously will be masked this main lobe. So we will try it. And now is difference between targets 500 meters. So we will put 400. You can see it is closer. Okay, I will speed up. 300, 250. Okay, done. Two targets, but only one is visible because second one is that one. And always, if you make some mistakes and put some parameters and you won't go to back, just use this presets, visible, invisible, because sometimes it's handy. Next one is sampling effect, 10 megahertz. Very, very hardly visible. If I will put visible, okay, where I what's do it if I changing sampling? What's happened? Everything is like in finer resolution. If you, because okay, I will put it to 5. Remember, this is just visualization of spectra. Now I put 5 megahertz. Okay, you can recognize, but you understand me. It is not nice spectrum. It is not to since function. Okay, you can maybe hardly recognize that will be since function, but you need to have a lot of experience. So then still since function hardly visible. 20. Okay, we can discuss it. Maybe 30 better, and 40. Okay, I know how I answer you now. It is just about resolution. If you don't need, if you want nice results, use higher sampling rate. If don't want and you don't need.
Sir, my question was, I understand this point, but I'm just saying, is there a rule of thumb? Like,
Yeah, I get you, but I still don't know answer about this rule, so I don't know. I just thinking about our measurement.
Because there are a lot of systems in, like when we are doing signal processing for military, they have a very tight requirement. So they want to keep the sample rate as minimum as possible.
Yeah.
Speed up everything.
Okay. I get your answer now. But you are in commercial zone, and you know why? It is just about money. Because it is about AD conversion. And military system always almost need work in real time.
Yes.
The lowest sampling rate. Because if it will be higher, you can't process in real time, or your AD converter will be so expensive that nobody buy it. Okay, so it is, you don't tell me first time that is commercial, so it is clear, it is just about money. and stability, and the important is that it's in real time. And of course, it is different if you want to process 40 million samples per second or 20 million samples per second. It will be about real-time processing. Of course, it is depends on your device. I don't know, but I'm pretty sure that will be only combination money and real-time processing.
Yes.
But I must say that never you can go, okay, lowers the possible, but I suppose that never go to limit, like
Obviously, limit obviously 2-3 times more than
it is very dangerous, goes to limit, because I suppose, okay, tell me, in your devices, you go to 1.5 multiplication of minimal sampling rate 2 times, or what?
So first of all, I don't have access to any devices, but what I'm planning to do, that whatever I'm doing calculation with, that should be usable for actual device.
Okay.
Actual device, their requirement is they need real-time processing.
Okay, one more answer that is good, I think. Now we are working in MATLAB, so I can put any value. But in reality, I need found AD conversion that fulfill my requirements. So please take. Oh, it's okay. It is just my laptop's off screen. It is just about it. So it will be okay. You will plan experiment.
Sir, my question is answered.
Yeah. Oh, thank you.
Question is answered.
So, is it clear? Can we continue from this application? Please play it during night. Maybe if you have question tomorrow, I will answer you during tea break or something. I didn't find a mistake in this, so I hope that will work for you. Maybe you will find some mistake. Sorry? Tea break. Okay, so tea break. Okay, we need to really speed up. It is too in detail. Never mind. Okay, so tea break. Can we make tea break only 15 minutes, not 30 minutes? So 15 minutes, please.